This conference will now be recorded.
Hello everyone, the topics that we are going to discuss: density and molar mass of a gaseous substance, Dalton's law of partial pressure in terms of mole fraction, Graham's law of diffusion, kinetic theory of gases, that is the postulates of kinetic theory, and if time permits, then Boltzmann distribution also we can see. So the first topic is density and molar mass of a gaseous substance. So ideal gas equation that we have obtained by combining three laws. Fine, that we have seen in the last class. Now, density and molar mass, if we want to find out from the equation PV equal to nRT, we can do so. So suppose density is given, we can calculate molar mass and vice versa. Now, what is density? Density is mass by volume. That is for any substance. This is the definition of density, mass divided by volume. So volume will be equal to mass by density. Now, if this is the case, from the equation, that is ideal gas equation, PV equal to nRT, now what we can write? Suppose keeping all these factors same, PV and RT, if I write this number of moles, which is N, suppose I am writing number of moles in terms of given mass divided by molar mass. Given mass divided by molar mass. Now given mass is W, molar mass is capital M. So in place of small n, now W by M is written. Fine. Now if I keep this M part here and bring this V, that is volume, in the right hand side, we will get W by V. Now W by V is basically mass by volume. So in place of W by V, we can write density D, small d. So D is equal to W by V. So that is why from the equation PV equal to nRT, just by replacing this number of moles in terms of given mass by molar mass is capital M, given mass is W, capital W. Fine, and slightly rearranging the equation, we are getting P equal to dRT by M. So from this equation, any, that is, there are total R is constant, fine, and P, D, T and M. So if one unknown quantity and three known quantities are there, we can calculate the unknown quantity. Fine. So here we have this equation, problem. The problem is saying that zeanion, which is a volatile organic compound, is a component of rose oil. So that is information about this compound, but the actual information which we will be using is density of the vapor of this compound is given 0.46 gram per liter. So look at the unit. Density is mass by volume. So unit is gram per liter. So per liter, this is the mass. And temperature is also given, which is 257 degrees centigrade. Pressure is given 100 millimeter mercury. From this information, we have to find out the molar mass of this organic compound. R value is given in liter atmosphere per Kelvin per mole. So here density is given, then temperature is given, pressure is given, right? We have to find out, and R value it is already known, and we have to find out molar mass. So molar mass, that is capital M, that we have to find. So what we will do, we will use the previous equation that we have just seen. But before that, we have to do some conversion because R value is given in liter atmosphere. So first thing that you have to do, you have to change this pressure, because 76, that is millimeter Hg to atm, this unit conversion we have to do. Now 1 atm is equal to 760 millimeter of Hg. That means when it is 100 millimeter of Hg, you just have to divide it by 760 so that you can get it in terms of atm. So this is pressure. Density is already given in gram per liter unit. R value given, and you have to convert temperature from degree centigrade to Kelvin scale. So that is why we are adding 273 Kelvin. So now it is 530 Kelvin. Now we can use this equation P equal to D dot RT by M. So here D is known, P is known, T is known, R is constant, only capital M we have to find out. So if you use this equation, P equal to dRT by M, or you can say capital M is dRT by P, just put all these values, that is 0.46, then 0.082, then 530 divided by pressure, which is 100 divided by 760. If we do this calculation, the answer we can get, which is 152 gram per mole. Okay, so that is the unit of molar mass, because molar mass we have to find out in gram per mole. So whenever you are solving any problem, you have to be very careful about the units, because sometimes suppose in this case, if pressure is directly given in ATM, you don't have to convert it, right? So it depends. So just read it carefully, which unit is given. If required, we have to convert the unit. That is, just in this case here it is given in millimeter Hg, and we have converted it to atmosphere unit. Which one of the following graphs is not correct for ideal gas? Here, first two graphs, D versus T. Then the third graph is D versus 1 by T. And the fourth one is D versus P. So basically, density is involved with temperature or pressure. Fine. So here what is D, what is P, what is T, everything is mentioned. You just have to choose which one is wrong for ideal gas. So which equation we will use? That we have just seen in the previous slide, P equal to dRT by M. Now if this is the case, here when it is D versus T, you have to consider that the other quantities are constant by default. Okay. So here D and T, if we focus on these two quantities, now I can write D is equal to Pm by RT. So this part if you fix, that is constant, D is inversely proportional to T, right? That means when D will increase, T will decrease, and vice versa. Now when we have two quantities that are inversely proportional to each other, what will be the nature of the curve? The nature of the curve will be this one, because it is not 2, because when one is correct, obviously 2 cannot be correct, because both are D versus T curve. You cannot say both are simultaneously correct, that is not possible. So when something is directly proportional, just any quantity, suppose I am saying x is proportional to y. In that case, when you have x versus y, it will be like this. But if I am saying that x is inversely related to y, that is proportional, in this case when you draw the curve, now it will be having this type of nature. So if that is the case, 1 is correct, 2 is not correct, and it is single choice. So we have reached the correct option, which is option 2. But what about 3 and 4? Why these two are also correct? We will also see that. So in this case, when we know that D is inversely proportional to T. Okay, but if you take directly this 1 by T, suppose I am writing this equation D equal to some constant K, then multiplied by 1 by T. So as if this equation is, if you compare with y equal to mx, so here D will be in y axis, x is directly 1 by T, x is not T, it is inverse of T. So slope is positive. So now it will be having this type of nature. So this is also correct. And what about 4? 4 is T versus P. D versus P. Now here, if you consider this equation, D and P, this part we have to fix. So D is now directly related to P. So it is directly proportional. And when anything is directly proportional, we have to follow this type of nature of curve. So that is why this is also correct. Only this one is not correct. Fine. So option 2 is the correct option, because in option 2 we have curve number 2, right? So which one of the following graphs is not correct? It is option 2, second curve. Another law which is known as Dalton's law of partial pressures. Here we have oxygen and we have nitrogen. So these two are separate. Now when it is oxygen gas, the pressure mentioned 159 millimeter Hg. When it is nitrogen, it is mentioned 593 millimeter Hg. So whatever is the quantity, this is the pressure. Now if you add these two, you are getting a mixture of oxygen and nitrogen. So in this case, the new pressure, this is very simple. You just have to add these two values. And that is actually Dalton's law of partial pressures. Here for simplicity, we have taken two gases, but it is true for any gases. Fine. So let's see what it says. So the law is the total pressure of a mixture of non-reacting gases. Now this condition is very important. Suppose you are mixing 2 or 3 gases or 4 gases, and they have the capacity to react with each other. So if that is the case, then this law is not applicable. So provided they are not reacting with each other, then only this law is possible. Because if they are reacting with each other, they will be producing something else. There will be reduction in their initial number of moles and so many things. This is complicated, right? So when it is not, they are not reacting with each other, that is non-reacting gaseous mixture, if you have, then the sum of partial pressure of the gases present in the mixture, that is actually the total pressure of the gas. Now what is partial pressure? So partial pressure of a component gas, it is the pressure that it would exert if it were present alone in the same volume and temperature. So what it's saying, so suppose here if you consider the third container, where basically volume for all these three containers are same, all are having same volume. So in the last case, you have mixture of these two. Now in this case, O2 will have some partial pressure, suppose it is PO2. Nitrogen will have some partial pressure, suppose it is PN2. Now this partial pressure, this is component number 1, this is component number 2. So partial pressure of first component, that is O2, it will exert, that is this partial pressure is actually the same pressure when N2 is not present. So that is this situation where only O2 is present. Here only N2 is present. So here PO2 is basically that pressure when it is present alone, not with any other gas. But remember, V and T, volume, temperature must be same. Then only it is, this law is applicable. So suppose we have taken three gases, gas number 1, gas number 2, gas number 3, and their corresponding partial pressure small p1, small p2 and small p3 in a container. Now when we have taken P1, P2, P3 all in the same container, now the pressure of this, that is after mixing, suppose it is P total, and P total will be equal to all these three values. So here only three gases are shown, but it is true for any number of gases provided they are not reacting with each other. If it is they are reacting with each other, then this law is not applicable. And this is known as Dalton's law of partial pressures. So now we will do some derivation. Partial pressure in terms of mole fraction. So we will try to see how partial pressure is related to mole fraction of gases. Now what is mole fraction? We will come to that one by one. First look at this equation. We know the ideal gas equation, PV equal to nRT. If this is true, I can write P equal to nRT by V. Fine. So suppose it is number 1 gas, that is pressure 1, small p1. Here we have changed the subscript of number of moles for the first gas, which is N1. Now these are constant. R is already constant and T and V constant, that we have already seen in the previous slide when we have stated the law. So you have to keep it constant. So for the first gas, the partial pressure is P1 and the corresponding number of moles for that gas 1 is N1. Similarly, for the second gas, it is P2 and you can write this equation M2 into RT by V. For the third gas, it is N3 and P3. Now what we'll do, we will add P1, P2, P3. So when you are adding all these three, you are getting P total. Now in place of P1, I will write N1 into RT by V. In place of P2, I will write N2 into RT by V. In place of P3, I will write N3 into RT by V. Now RT by V you can take common. So you are left with summation of the number of moles of these three gases. Now this you can write in terms of total number of moles, which is N subscript total. So now we have reached a new equation, which is P total is equal to N total into RT by V. Okay, just keep it aside. Now come to mole fraction. What is mole fraction? Now mole fraction we express with X, this type of quantity. Okay. So mole fraction means, suppose for gas 1, if I am saying it is mole fraction of the first gas, it is X1 and that will be equal to number of its moles, that is the first gas, remember number of moles N1, divided by all the number of moles, that is N total. Or you can write N1 plus N2 plus N3. So this is the mole fraction of the first gas. So here we have mole fraction of the first gas, N1 divided by this. So here dot dot sign is given because it may be true for any gas, any component. Here we have chosen only 3. So after all, it is N1 and N1 divided by N total. Next, what we'll do, if X1 is equal to N1 by N total. Okay. Now, from this equation, just consider the first equation. P1 is equal to N1 into RT by V. If this is true, you can also write the same equation like this. Just bring N1 in the left hand side and bring P1 in the right hand side. Okay. So N1, sorry, I mean to say R1 and RT by V, it will be P1 divided by RT by V. So if that is the case, now similar thing you can also do for N total, because you can write N1 like this, you can also write N2 like this. So N2 will be equal to P2 divided by RT by V. So when you are adding all these three, N1, N2, N3, basically you will get this quantity, and another quantity, which is P3 by RT by V. So in this case, RT by V in the denominator is common, and in the above part, that is numerator, there will be P1, P2, P3 summation, which is nothing but P total. So we can write this equation, that is total number of moles, that is equal to total pressure divided by RT by V. Basically this portion is nothing but a constant, because temperature constant, volume constant, and R is already universal gas constant. Now what we'll do, this is suppose equation number 1, this is suppose equation number 2. So just divide equation 1 with 2. Left hand side it will be N1 divided by N total. Now N1 divided by N total is nothing but X1, isn't it? Now put individually the value of N1, which is this, and in the denominator N total put from equation 2 P total by RT by V. So these two part, it will be cancelled. You will be left with P1 by P total. So ultimately what equation we are reaching? We are reaching that P1 is equal to X1 into P total. Okay, so this equation will help us to solve some problem. Similarly, it is also true for other components. So in general, I can write that P for any component, suppose any component, I'm writing Z here. So it will be mole fraction of Z into P total. So it is true for any component which is present in the mixture. Fine. That means this partial pressure, that is equal to total pressure multiplied by its mole fraction. Or in general, I can say that partial pressure of a particular component is equal to mole fraction of that component multiplied by total pressure. Okay. So here, this is the final statement we can make. Partial pressure of a gas is obtained by multiplying the total pressure of mixture by mole fraction of that particular gas for which you have considered the partial pressure. So it is true for any component. Here we have a problem related to this. We have mixture of hydrogen and oxygen and contains, that is this mixture of H2 and O2, it contains 40% of hydrogen by mass. So with respect to mass, out of 100, 40% is mass of H2. So rest of the portion, that is 100 minus 40, 60%, that will be the mass of O2. So this is first information. And pressure is given 2.2 bar. From this information, you have to find the partial pressure of the first component, which is hydrogen. We just have two components, H2 and O2. So if we consider mass, here it is given 40%, but suppose I am considering this unit, it is gram. So 40, you can also write unit, it doesn't matter. Any unit you can consider. So weight of H2, it is 40 gram when the total mass is 100 and O2 is 100 minus 40 because we just have two components, right? Now, how you will get number of moles of H2? If you divide this 40, which is given mass, divided by its molar mass, which is 2. So this is the number of moles for H2. Similarly, for oxygen, 60 given mass divided by, you have to consider the mass of oxygen, 32. Okay, so 60 by 32. So in this way, we can get the number of moles. But you can also put it directly. So here, this is X of, that is mole fraction of H2. This is mole fraction of H2. Now mole fraction of H2 is number of moles of H2 divided by total number of moles. Now total number of moles, that is we already have seen, this is basically N of H2 and N of O2 is, so just put it here, in place of NH2 it is 40 by 2, this is also 40 by 2, this is 60 by 32. Final calculation will give this value 0.914. So this is the mole fraction of H2. Okay, and if you that is, suppose in the same problem, if you also have to calculate mole fraction of O2, though it is not required here, but suppose I am saying, suppose you also have to find out XO2, what you can do, just simply subtract it from 1 because it is fraction. So when there are two components and you know the mole fraction of the first component, obviously the total mole fraction, it is, if you add all the mole fraction, it is 1. So the remaining component, its mole fraction will be simply subtract it from the value 1. So it is only for when it is two component. Okay, so suppose if it is 3 component, another gas is also there, N2. So if you want to get mole fraction of O2, you just have to subtract mole fraction of H2, N2 from 1. Then only you can get mole fraction of O2. Or you can also do the same calculation that you have done for H2. That also you can do. Fine. So now we have reached the mole fraction of H2. Once we have reached the mole fraction of H2, next we have to find out the partial pressure. Now it is very simple. Remember in the previous slide what we have obtained. The final equation, That is partial pressure of a gas that you can obtain if you multiply the total pressure with its mole fraction. So you know the total pressure, which is already given in the question, 2.2. You also know what is the mole fraction of H2. So rest of the work is very simple. So partial pressure of hydrogen, fill in the blank, we have to write partial pressure of hydrogen, which is mole fraction of hydrogen into total pressure. So 2.2 multiplied by this, it is 2.01, nearest integer is 2. So answer is 2. It is an integer type of problem. Next question, 0.5 moles of gas A and X moles of another gas which is B. So we know exactly what is the mole fraction of A, but for the other component it is given in terms of X. They are exerting a pressure of 200 Pascal in a container having volume 10 to the power meter cube, temperature 1000 Kelvin. R value is given in joule per Kelvin per mole. Basically, it is 8.314. So here pressure is given in Pascal, volume is given in meter cube. So you have to constant the SI unit of universal gas constant. Okay. Now we have two component A and B. Component A, total moles it is given, but for the second component we do not know what is the corresponding number of moles. So that actually we have to find out. So X is any of these four options, which is in terms of, you can see this universal gas it is given. Basically you don't have to write the value of R, because in the option the answer of X, that is actually in terms of R. So we don't have to write R value. Here total number of moles, simply add the number of moles of A, number of moles of B. This is ideal gas equation. So now what we'll do, just put the value of P, which is 200 Pascal, put the value of V, which is meter cube, and here R is, that is direct value, you don't have to write, but just be careful about the unit. It is joule per Kelvin per mole. Pressure and volume it is in terms of Pascal and meter cube respectively. So suppose if it is given in liter, you have to change it to meter cube, otherwise it will be wrong. But here it is directly given in meter cube, so we don't have to convert it. Fine. And in here N is basically N total, because we have mixture. R we will not put any value because result will be in terms of R, and temperature is 1000. So from this calculation we can find the value of X, which is this one. So option C will be the correct option. So after this partial pressure law, next we have Graham's law of diffusion. When two non-reactive gases are allowed to mix, okay, so in the previous case also we have seen, we have taken non-reactive gases also. Here also the same thing, you have to take non-reactive gas mixture. Then the gas molecules migrate from region of higher concentration to a region of lower concentration. Okay, so when you have just added it first in a particular container, obviously at initial, that is just at a first, when you have just mixed it, it will not have homogeneous concentration. There will be at some part it will be high concentration, and other part it is low concentration. So what will happen once you have this mixture, there will be migration of these gas molecules, and the direction is from higher concentration towards the region of lower concentration. So this property of gas, which involves the movement of gas molecules through another gases. So one gas, suppose gas number 1, its molecules are moving through the gas molecules of the second gas. This property is known as diffusion. There is another term which sounds similar, which is known as effusion, but it is slightly different. Effusion is also another process which is used for gas, but here its definition is This process where a gas escapes from a container through a very small hole. So suppose you have kept a particular gas in a container and there is a very small hole. So what will happen? The gas will escape very slowly through this small hole. And that process is effusion. So there are two processes, diffusion and effusion. Now this law, Graham's law is saying, though it is called Graham's law of diffusion, but it is also applicable for as well as for effusion at constant temperature and pressure. So these two must be constant. The rate of diffusion, in bracket it is also mentioned effusion. Rate of diffusion of gases, it may be any number of gases, it is inversely proportional to the square root of their densities. Suppose you have taken two gases. For the first gas, it is density D1. For the second gas, it is density D2. And the rate of diffusion for the first gas is R1. For the second gas is R2. So in that case, what will happen? So as it is mentioned, it is inversely proportional to square root of density. So it will be 1 divided by root over D1. Okay. Sorry, it's not. So it is R1 proportional to 1 by root over D1. Similarly, if you remove this proportionality sign, you have to put a constant K. This is equation number 1. Similarly, for second gas also, R2 is proportional to 1 by root over D2. If you remove this proportionality sign, you will get a constant which is K by D2. Now for both cases, this constant is same. So this is equation 1, this is equation 2. So what we will do, if you divide equation 1 by 2, in the left hand side it will be R1 by R2, and in the right hand side K and K will be cancelled. So dividing equation 1 by 2, we will get in the left hand side R1 by R2, in the right hand side K and K will be cancelled. So ultimately it is root over D2 first, then D1, because it is inversely related. Temperature, pressure same. Now you can convert this D term to molar mass also, that is molecular. So for gaseous molecular weight, it is approximately equal to 2 into vapor density. Fine. So vapor density is basically this density. That means M is equal to 2D. So D you can write as M by 2. So in place of D2, now you can write M2 by 2. In place of D1, you can write M1 by 2. 2 will be cancelled, and after all, you are getting a new equation which is also equal to this ratio R1 by R2, but now it is in terms of molar mass, it is not in terms of density. So R1 by R2, it is equal to root over D2 by D1 as well as root over M2 by M. Both are fine according to this law. A bottle of ammonia, NH3 gas, and a bottle of HCl, hydrochloric acid. They are connected through a long tube. So suppose we have a bottle where ammonia is kept and it is connected to another bottle where HCl is kept. Okay. Now that is, it is connected like this through a long tube. That is, their cap is opened simultaneously. So it is also open, this is also open at the same time, simultaneously at both ends. Now we know that when ammonia reacts with HCl, NH4Cl is produced. That means this gas will come to this direction, HCl gas will come to this direction, and at their meeting point, when they will be coming in contact with each other, then they will produce the product NH4Cl, that is white dense fume, that is the appearance, and the name is ammonium chloride. Now this white ammonium chloride ring, that is the dense fume in form of ring, that will be formed. Which option is correct? Is it at the center of the tube? So this is, suppose this is the tube This is the point of ammonia. This is the point of AC. So that is the product formation that you can easily see with naked eye, because it will be in the form of some ring, because it is connected by tube which is circular. So the fume, it will also be in the shape of ring. Now this ring, as the tube is transparent, you will be able to see it. So is it at the center of the tube, or is it near the HCl bottle side, that is right hand side, or is it near the ammonia side, that is left hand side, or another option, throughout the length of the tube, that is it will be all over the tube. Now which one is correct? Now this problem is related to the previous law that we have learned, and according to that we have seen that rate, that is inversely proportional to the root over of its molar mass. That means the gas which is having higher molar mass, its rate of diffusion, it will be low, because it is inversely related. It is true there is a root over sign, but relation is inverse. So when mass is high, rate is low. Now among ammonia and HCl, you just have to compare the mass. For ammonia, the mass is 17, nitrogen is 14, and 3 hydrogen, that means 3 plus 4, so it is 17. And for HCl, it is 1 plus 35.5, that means it is 36.5. So HCl is having higher molar mass. If HCl is having higher molar mass, so the rate of HCl, it will be lesser than the rate of ammonia, because ammonia is having lesser mass, molar mass. Okay. Now if that is true, that means when, let me use another color. So when ammonia, that is at the same time, suppose you have just opened the two their cap, and when ammonia will reach the distance at the same time, HCl cannot reach the same distance because rate is. So obviously their connection point will be, if it is center, suppose this is center, their connection point will be somewhere here, that is close to HCl, because when ammonia is moved this distance, HCl is able to move only this amount. I'm just saying arbitrarily. So it will be close to the bottle of HCl. Which option is correct? It should be B. So rate of diffusion is proportional to 1 by root over m. Here mass is given 36.5 for HCl and 17 for ammonia. So rate of diffusion for ammonia is high because its mass is less. So this should be the correct option. Okay. At identical temperature and pressure, T, P both are fixed. Rate of diffusion of hydrogen gas is 3 into root over 3 times that of a hydrocarbon. Which hydrocarbon, that is not mentioned, but its formula is like this. Cn, hydrocarbon, that means you will have only carbon and hydrogen, and if n is the total number of atoms of carbon, total number of atoms of carbon, then total number of atoms of hydrogen is 2n minus 2. So from this information, you just have to find out what is the value of this subscript, that is the total number of moles of carbon. N value you have to find. So this is also related to diffusion. So rate of hydrogen and rate of this hydrocarbon, suppose it is R of H2 and R of hydrocarbon, I am writing carbon and H, but you can write it like this. So if you take their ratio, it will be this times, which is already given in the question. So that you can write, fine. So we can write here rate of H2, here different sign is used, but that doesn't matter, you can consider as if it is R. So rate of H2 divided by rate of this hydrocarbon mentioned in the subscript, this is actually root over 3 into root over 3. Now we know that rate is equal to, that is mass of, so here this m is basically molar mass. So R is proportional to root over molar. That means when you have taken in the numerator, if you have taken H2, obviously in the right hand side it will be molar mass of the hydrocarbon first, then it is the mass of H2. So now, because you do not know what is the molar mass of hydrocarbon, just keep it like this, but you know for hydrogen. So that is, you can write here 2. Once you have mentioned this, from this equation you can easily find out what will be the molar mass of this hydrocarbon from this equation. You just have to remove this root sign, both sign. So you have to do squaring. So squaring on both sides and slight rearranging, you will get the value of, that is molar mass of this hydrocarbon, which is equal to 54. Now there are total n number of carbon. That means it will be n into 12. There is total 2n minus 2 number of hydrogen. That means you just have to multiply 1. Now from this equation, you can finally reach the value of n, which is 4. So it is matching with this option. Right? So at a first glance, it seems very difficult, but logically, stepwise, you have to think. First, just try to see what are the informations that are given. Okay. So from this information, step by step, you have to reach the final answer. Kinetic theory of gases. There are basically some postulates for this theory of gases. But before that, let's see these some information related to kinetic theory of gases. All the gas laws that we have already learned. Remember Boyle's law, Charles' law, Lussac's law, etc., etc. All these gas laws are basically some concise statement of some experimental facts, isn't it? All these are experimental observation. We have also seen the graphical representation, okay, that are observed in the laboratory, and though we have done it from experimental observation, but a question may arise that why the system is behaving in that way. And remember, all the gas laws that we have learned, they are applicable for any general gas. It has to be that is behaving ideally. That is the condition, but you can apply it for any gas. It is not restricted to any particular gas. That means, as it is true for any gases, it means there must be some property of gases that are common for all the gases. Then only it is possible, right? So for example, these gas laws, obviously they help us to predict the pressure increase when we compress the gas. But it is just one example I'm saying here. So suppose when you have kept the temperature constant, then you are changing the volume, what will be the effect on pressure? That we can predict from Boyle's law. Okay, that is a macroscopic observation, overall observation. But what about if we think from the molecular level, microscopic level? So suppose you are compressing the gas, that means you are decreasing the volume from initial volume to final volume, you are decreasing because it is compression. And we know when you are decreasing the volume, there will be increase in pressure because these two are inversely related according to Boyle's law. But what is actually happening in the molecular level, microscopic level? What is the effect on the individual molecules? That is the question. Generally, in case of solid and liquid, for these two matter of states, the physical properties, how we can describe it in terms of size, shape, mass, volume. But for gases, what happens? There is important difference that mass and volume we cannot measure directly because of lack of their definite shape and size, which is possible for solid liquid but not possible for gases. So mass volume you cannot measure directly. But one point which is good, that is beneficial for gases only, that is their common behavior for different gases. Common behavior, that means all the gases there are some common behavior. So it proves that the internal structure of all the gases, there must be some resemblance. If there is no such resemblance, we cannot have all these gas laws based on experimental laboratory observation. So this type of common behavior, on the contrary, you will not find for solid and liquid. It is true that for solid liquid you can easily find the physical properties, shape, size, mass, all these are fixed. But for gases it is not fixed. But for gases one thing is unique, which is not, you will not get for solid and liquid, and this point is their behavior is common. So that is why you can apply all these gas laws. Fine. And it is possible because similarity in the internal structure. So kinetic theory, which you can say it is basically a mental model. Kinetic theory, which is basically a mental model of gases, it helps us to gain clarity on these observations. That is the observations based on which you have all these gas laws. Fine. The basic idea here that the gases are essentially composed of freely moving molecules. We know compared to liquids and solids where the molecules or atoms, they are close to each other, but in this case the space between individual atoms molecules, it is very high. So because of these freely moving molecules, this type of nature, that is all the gases are essentially composed of this type of individual particles that are freely moving. That is at the root of this kinetic theory of gases. So this theory is developed as a result of thoughts and contributions, and it is not that it is a single day event. That is, different people have done it, different many scientists, and it is the observation over the centuries. So you can understand how much research is done on this. Fine. So one by one, if we see the postulates, though we will not be able to finish, but 2 or 3 postulates we can see. Gases consist of large number of atoms or molecules. That is fine, easily understandable. And these atoms or molecules that are so small and so far apart on the average, unlike solid or liquid, that the actual volume of the atoms or molecules, you can consider it negligible in comparison to the empty space between them. So suppose this is the container in which you have all these molecules. Fine. Now this is the space between 2 molecule or atom. Okay. Now this space is very large. So it is saying that suppose in this container there are total 10 particles. Now these 10 particles, individual particle, if you see, they are far from each other. So this distance is very large. So if you separately consider, suppose you are just considering the volume of the atoms or molecules, that is volume of the particles. That is one volume. Another volume is just the that is space that is present in between them. That is another volume. So suppose the first volume is V1, the second volume is V2. So obviously V2, that is the actual empty space present between them, that is far greater than the volume of the total particles. Okay. So this is the assumption we can make, that the volume of the atoms or molecules, that is V1, it is negligible. It is so small compared to V2, which is the volume or empty space between them. You can neglect it. So V1 is negligible compared to V2. Second postulate, there is no force of attraction between the particles of a gas when it is at ordinary temperature and pressure. So one particle and then another particle, there is no force of attraction. Fine. And the support of which comes from the fact that gases can expand and occupy all the space available to them. So in this case, you have this square shape container, you have kept it. But suppose you have taken a large container compared to this, and you have kept the same amount of gas. Now there will be some expansion. Now this expansion, quick expansion, and they will occupy all the space. So from this container, now you have given a large container. So obviously now the space between the individual particles that will increase because total number of particles same. And because of the diffusion property, they will occupy all the space available. Homogeneous distribution will be there. And why it is possible? It is possible because initially there is no force of attraction. Because if there is force of attraction present between two particles, separation of them, it is not so easy. But once you have kept in large container, now they are far from each other. Why it is possible? Because there is no force of attraction. So this fact, the support of which comes from the fact gaseous can expand and occupy all the space you will be given to them. Fine. The particles within a container, they are in ceaseless chaotic motion, colliding incessantly, without any rest, incessantly with each other, and not just with each other, they are also colliding with the walls. So if you look at the picture carefully, you will see. So here this particle, suppose it is colliding with these walls. So this sign is basically it is symbolizing that there is some collision happening. Similarly, when it is colliding with each other, then suppose it is colliding with this one. So that is another type of collision possible. So they can collide with each other and also with the walls of the container. So bombardment of these particles on the walls of the container, that is actually responsible for the pressure that we get. We know we use pressure for gas in a container. So how this pressure is arising? Because they can collide with the walls of the container, and that is giving rise to pressure. Pressure is average force per unit area per unit time. So suppose if you have considered any particular area in the wall, so per unit area per unit time, the average force, that is actually the pressure. Okay, so in this way pressure will be generated. Now these collisions, that is collision between two particles or collision with the wall, they are perfectly elastic, and how it is understandable? As total kinetic energy before and after the collision remain the same, though their individual energies may change. So suppose you have, for simplicity, I have taken total 3 particles. So they are colliding with each other and also with the walls of the container. So because of this type of collision with each other and the walls, it is completely elastic. And as it is elastic, so that is the reason that the total kinetic energy before and after the collision remains same. That is overall kinetic energy, total. But if you individually consider the kinetic energy, that may vary. That is individual kinetic energy of 1, of 2, of 3, that may vary. But total kinetic energy is fixed before and after collision. So that is why you can say that collisions are perfectly elastic. If there were loss of kinetic energy, it means motion of the particle will stop. So they have, that is, there is some as if removal of energy from this particle. So now they are not in such motion as before. They have lost the energy, kinetic energy. So their motion one time will reach when they will be still, motion will be reached, and the gas molecules will be settling down. But that is not actually we observe. So it is also another proof that as kinetic energy is not changing, it is a proof that collision should be perfectly elastic. Okay. At any particular time, different particles in the gas have different speed. So suppose here we have taken particle 1, particle 2, particle 3. At a particular time, it is not necessary that 1, 2, 3 they will have same speed. No, that is not necessary because their kinetic energies are different. Okay. It is possible to show that though the individual speeds are changing, it is not fixed at a particular time. The distribution of their speed, that remains constant at a particular temperature. Now what it means by distribution of speed, that you will be able to understand once we will see a graph related to this, the graph of speed, that is fraction of molecules versus speed. So probably we'll see that in the next class. So right now just remember this fact, that it is possible to show that individual particle speed, it is not fixed. For one it is v1, for two suppose it is v2, then v3, but that the nature of distribution of speed, that is similar type, it is constant at a particular temperature. Then you change the temperature, there will be another type of distribution. Okay, so we have some time left. If a molecule has variable speed, then it must have a variable kinetic energy. That is why average kinetic energy we should consider. In kinetic theory, it is assumed that average kinetic energy of the gas molecules is directly proportional to absolute temperature. That means temperature in Kelvin scale, not just any scale. Only when you consider absolute temperature, this average kinetic energy is directly proportional. And that is also supported by the fact that when you heat a gas, provided volume is constant, we know pressure increases. Remember, when volume is fixed, how pressure is changing with temperature, that law we have seen. So pressure increases. So it means when you are heating the gas, basically you are providing thermal energy. So kinetic energy of the particle will increase, and now they can strike the wall of the container. That frequency will increase, right? So more frequently now they will strike. More frequently when they are striking the wall, that means pressure will also increase. Fine. So we will see the graph related to this theory, and also how these postulates, they can explain all the gas laws that we have already discussed in last class, that is P versus V, P versus T, V versus T, how it is related to these postulates, that also we'll see in the next class. We are at the end of the session. Thank you for listening.